Unifying margin-based softmax losses in face recognition. The standard classification loss is given by the softmax of the correct class logit over all class logits. When the image feature vector and the class prototype vectors are normalized, dot products equal the cosine of the angle between the vectors, and the loss can be rewritten in its angular shape. Researchers in the literature field introduced margin penalties in the angle of the correct class in order to push the correct class decision boundaries, so to make classification harder, hoping that it will translate into final model performance that is higher. Sphere face and later arc face and cos face studied different formulations of this margin penalty, whether additive or multiplicative, introduced in the angle space or in the cosine space, which can really be thought of different ways of modulating this cosine phase by changing its period, phase, vertical shift. This begs the question of asking and studying how an amplitude parameter would result into better model performance compared to the other margin formulations. In studying so, we notice that aggressive values of this multiplicative margin would lead to local minima of the loss that correspond to degenerate configurations, which we call polar collapse, a phenomenon where all the prototypes converge to a single point in the hypersphere, and all the feature vectors corresponding to the images converge to the antipodal point in the hypersphere. When we regularize in order to enforce that the prototypes are uniformly distributed in the surface of the sphere, we are able to train a model with this margin formulation to convergence. When compared to arc face and cos face under a standard schedule, it seemed that arc face performed better of the standard benchmarks of megaface and LFW, perhaps corroborating this general accepted hypothesis that a linear separation in angular space is the reason for the success of arc face over the other margin formulations. However, a longer training schedule where models are trained to convergence shows that these different margin formulations do not differ in a statistically significant way. When we look at how margins affect the loss curves as a function of the correct class angle, we notice that margin penalties make correct classification harder by pushing the decision boundary, and in doing so, decreasing the intra-class distance. Notice, however, that optimal margins do not minimize intra-class distance. A careful theoretical study under the assumption of a uniform distribution of the prototypes show that the optimal values of the margin correspond to the margins that move and shift these curves so that intra-class distance equals 1/2 of the interclass distance, a hypothesis we call the half-angle hypothesis, which would enable a selection of an optimal margin theoretically without expensive tuning. For any questions, meet us at the poster session, and thank you for your attention.